Okay, let's get started. Hi, everyone. Welcome to the Space Science webinar series hosted by the Center for Space Science at NYU Abu Dhabi in collaboration with the UAE Space Agency. Today's speaker is Reem Faris. She's an assistant professor at the UAE University in Al Ain. She's an observational astronomer interested in studying magnetism in cool stars. She works on star-planet interactions, modeling planetary environments, and her talk today will be on star-planet interactions. Before this, she has worked at the Lebanese American University in Lebanon, at the University of St. Andrews in the UK, and at INAF in Italy. And so, Reem, welcome to our center virtually, and the stage is all yours.
Thank you so much, Dimitra, for the introduction. I will share my screen with you. So thank you again for having me. It's a pleasure to be talking to you today about the work I've been doing, which is understanding and investigating star-planet interactions, and in particular in the case when we have a planet orbiting close to a star. So just as a very, very general introduction, I would like to present the solar system, which is the most known planetary system we have, of course. This representation of the solar system is not to scale, obviously, but there are a few things that I want to speak about really briefly. We do have the sun that is the central star, obviously, and we have planets around it. In our solar system, the first 4 planets, we call them the inner planets, they are rocky and small, and the big planets we have, or the gaseous planets, the outer planets, are indeed gases and big. So for a long time, we had hypotheses of how planets form, how they migrate, what happens actually when the whole process is taking place. And of course, we thought that big planets would form far away from the star and smaller planets could form closer to the star. So just to mention Jupiter, that is the closest big planet we have in the solar system to the sun. It is at a little bit more than 5 astronomical units, of course, 1 astronomical unit being the distance from Earth to the sun. So indeed, it is further away than the small and rocky planets we have. Now, this was the idea we have of planets until we discovered the first exoplanets. And the first exoplanet around a solar-like star was discovered in 1995, so about 25 years ago. Currently, we have more than 3,000 confirmed exoplanets. And when we speak about exoplanets, these are planets orbiting stars other than the sun. So when you go out at night, you look at the sky, you see stars, you do not see planets, but there are planets out there orbiting these stars. The very interesting thing about those exoplanets that were discovered is that actually they have diverse properties when we speak about their mass, when we speak about their composition, and also when we speak about their orbit, how far they are from the star, the eccentricity of the orbit, etc., etc. So just to give you an idea, I am presenting here the planet mass as a function of Jupiter mass, in Jupiter mass actually, as a function of the separation in astronomical unit for all the discovered exoplanets. Every single dot you have here is a confirmed exoplanet. The colors indicate different techniques of discovery of the exoplanet, but we don't really need to worry about that. And what I want you to take out of this plot is actually we do have a very diverse picture of exoplanets, let's say, from not very massive exoplanets to very massive exoplanets in terms of Jupiter mass, but also from very close exoplanets to their star to very, very distant exoplanets from their stars. So one thing that is also very interesting is that if we look in this diagram and if we decide to consider a separation or a semi-major axis of 0.1 astronomical units, we do see actually a lot of planets laying here. So of course, one would argue that our discovery techniques, or the techniques we use to discover these exoplanets, are biased towards some of these exoplanets. But the interesting thing is that these exoplanets exist in the first place. Of course, currently with all the space missions and with all the advancement in technology in the 25 years, from the first discovery till now, we do have different masses that were discovered very close to the star. But originally, when we started discovering exoplanets, a lot of these exoplanets were in this region of this mass separation diagram, and we call them hot Jupiters. So why do we call them hot Jupiters? Because simply those planets are similar to Jupiter in terms of mass. So they could have masses more than 0.1 Jupiter mass, but they are extremely close to the star. So the separation, usually we consider it to be less than 0.1 astronomical unit. And just to give you an idea, it means actually that you have Jupiter, something similar to Jupiter, but 50 times closer to the sun. So if we are considering what it means, it's just a small sketch to make things like more clear. This is one of the very famous stars I will be talking about later in this talk. It's HD 189733. This is the star and the exoplanet around it. And this system is well known, but the idea is that actually the exoplanet, this is the orbit of the exoplanet. If you compare it in our own solar system to the orbit of Mercury, this is where this exoplanet is compared to Mercury, not even compared to Jupiter, compared really to Mercury. So we are talking about extremely close distances to the star. And on another hand, if we just want to imagine for a second that our Jupiter was a hot Jupiter, you would see actually this picture here. So this is the sun during a solar eclipse, and we can see clearly all the corona and everything happening with the solar wind of the sun. Jupiter, if Jupiter was a hot Jupiter, it would be somewhere here. So extremely close to the star, actually almost at 8 stellar radii. In these systems, obviously, we can think that there are many things happening that we call them star-planet interaction. So because the planet is very, very close to the star, of course, the planet is strongly irradiated. And there are a series of papers in the literature that studied this kind of like irradiation from an observational and a more theoretical point of view. Here I listed just some of them. But in addition to the fact that the planet is irradiated, of course, the planet, as I showed you before, in case Jupiter was a hot Jupiter, is extremely close to the star. So we can imagine also that we do have some kind of magnetospheric interactions between the planet and the star. So the planet is actually almost embedded in the magnetic field of the star. And we can imagine that we might have reconnection events taking place. If the planet is magnetized, we can have interactions between the magnetic fields. And it was suggested really early in the literature when these star-planet interactions, this field started actually, that those kind of magnetospheric interaction, they might affect the star. So you might have particles falling back on the star and you might have chromospheric heating. And I will be talking about it in a bit. A third way of interacting between this massive planet and the star close to it is, of course, tidal interactions. This is really a picture of the Earth and the Moon, but it explains what it is. So, you know, you have a massive planet because we're talking about Jupiter masses, and you have a star next to it, very close to it. So you would have tidal interactions. Now, it's very nice to say, okay, we do have all these kind of interactions, but the idea is, how do these interactions affect the system? And of course, the way they affect the system, they could affect the planet and they could affect the star. And I'm going to list that in the next 2 slides. So if we are talking, and I'm listing only some effects actually, if we are thinking about what kind of effects star-planet interaction would have on the planet, of course, when you think that the planet is really highly irradiated, we can think that the planet, the atmosphere of the planet could evaporate. So the planet could actually see some evaporation to its atmosphere. It was observed, so this is something that was observed, and for some planets, we could also observe like a kind of comet, like a tail, comet tail, you know, around the planet because of the motion of the planet. We can think that when there is an interaction between the magnetic field or between the stellar wind and the planet, we could see some aurora happening on the planet that will lead to some radio emissions. So if you observe in the radio frequencies, maybe you could see these kind of interactions. When we speak about the tidal interactions, some of the planets that were discovered were found to be quite big relative to what we would expect. So in comparison, for example, to Jupiter. And it was suggested that we do have some tidal heating. So because of the tidal interactions, the planet could heat and become a little bit bigger. Of course, this is a debated subject in the literature in a way that maybe it does not explain alone these sizes, but yet it could contribute to that. And we could have some influence of the tidal interactions on the planet through the orbital evolution of the planet. But the tough thing is that it's hard to observe the planets. It's much easier to observe the star. So let's try to understand what kind of effects star-planet interactions would have on the star. We could have an effect on the rotation, and there was studies, well, suggesting that some planet hosting stars could have an accelerated rotation because of these tidal interactions. It could affect actually the stellar inclination because of some tidal instabilities. But if we think about magnetospheric interactions, we do have an effect on the stellar, or we could have an effect on the stellar activity. And the stellar activity, usually the way we see the stellar activity, like we see on the sun, it is modulated by the rotation of the star. However, if you have star-planet interaction, it was suggested that you would see a kind of spot or something related to the activity that would move with the planet if we have a magnetospheric interaction, and it would be modulated by the orbit of the planet divided by 2 if you have tidal interactions, because you would have 2 tidal bulges. But in addition to that, something that is extremely important is the magnetic field of the star. Actually, the magnetic field of the star, it could be affected by all these kind of interactions, the way it's generated. But most importantly, the magnetic field of the star is a key element in all these kind of interactions, especially magnetospheric interactions. So it is extremely important to study the magnetic field of planet hosting stars if we want to understand star-planet interactions. So the way, again, how do we study them? Because the title of my talk is how do we investigate those star-planet interactions? You could take 2 paths, from a stellar perspective and a planetary perspective. If you want to study the star, you could study, as I just told you, the magnetic field of stars, study the general characteristics of the magnetic field of stars. In addition, you can study the stellar activity. So when we are talking about stellar activity, we're more talking about spots and small-scale magnetic field. You can try to look for X-ray excess, for example, from the stellar corona, indicating reconnection events or some events related to the planet. From a planetary perspective, you can go into radio emission. You can try to look for radio emission of the planet. If you observe the planet in the UV, for example, you could look for some bow shock formation and similar things. But there is also, like, if we want to study star-planet interaction, we could go actually for 2 different approaches, I would say. You could either decide for a statistical approach where you observe many planet hosts. And this is something we have done with some of our colleagues, where we observed 10 planet hosting stars. 10 is not a huge statistical sample, but I'm going to tell you why only 10 were observed just in a bit. But you could also go or decide to go for a multi-wavelength observation of some particular systems. And this is also something that we have been doing with some of our colleagues in a program called MOVES, multi-wavelength observations of an evaporating exoplanet and its star. And when you combine all these things, when you combine especially the multi-wavelength observation, you could hope that you will see a clearer picture of the whole system, or what to expect, what kind of emission to expect from these systems. So I'm going to start by telling you a little bit about stellar magnetism, or planet host stars. What kind of magnetic field do they have? And just to start with that, I'm aware that not many people do magnetic fields. So I would like to introduce how do we study magnetic field. It's not actually very straightforward. In a way, it's not like similar to photometry, for instance. You cannot just use something and you have the whole magnetic map of the star. But you can use the physics that we know and reconstruct the large scale magnetic field of the star. So the problem, what I would call a direct problem, is really simple. If you have a magnetic field, if the star is magnetic and you have a magnetic field where the spectral lines are formed, so on the surface of the star, you would have Zeeman effect. And this is an example here for the sun, where you have a sunspot, you have the slit of the spectrograph. And if you look in your spectra, you do see actually one spectral line at the level of the spot. It will split into 3 because of the Zeeman effect. What's very interesting in this is that actually those new lines that are formed, they are polarized. So you can study the polarization in the spectral line, and it's easily done using a spectropolarimeter, which is a spectrograph plus a polarization unit in the spectrograph. The polarization in the spectral lines will depend on few things. One of them, of course, is the field orientation, and then the rotational phase. And let me just explain it in 1 or 2 seconds. Actually, if you take one picture, let's assume you have a star, there is a spot on the star, and you take one picture of the star. Okay, this is one spectrum. So the one spectrum is a 1D image of the star. So if you have your spot, you might, in your intensity spectra, this is the intensity spectra, you would see a signature of the spot, but it will actually tell you where is the spot in longitude. It will not tell you where is the spot in latitude. So it is a 1D image of the star. The idea, if you want to reconstruct the full map, the full magnetic map of a star, what you would need then is a time series of spectra. So you take many spectra when the star is rotating, and you can recover the longitude and latitude of the spots. This is when we are talking about spots, but again, what I'm talking about is magnetism, the general magnetic field on the surface of the star. So we could use actually the polarization rather than the intensity spectra that is the usual spectra that we use. And this hopefully explains how does that happen. So what you see here, you have a star. On the surface of the star, we have a region that has a magnetic field. It's a radial magnetic field. It means it is pointing toward you, all right? Clearly, what you have done, this is the polarization, the circular polarization profile that you would get if you are observing the star. If we are at this stage with no magnetic region, we do not have any polarization. Okay, your light would not be polarized. Now, if you see the region appearing and then it will move, we can see clearly that we have a polarization signature. The polarization signature will travel depending on the longitude of the spot. And if it is a radial spot, we can see clearly that the signature will not change somehow polarity, let's call it. So it will keep the same shape and will travel across the line. If on the other hand, you have azimuthal magnetic field, so it is the toroidal magnetic field, you also will observe some polarization, some circular polarization, but you can see clearly that here the circular polarization is going to change when the star is rotating, because at the first part, the field is pointing toward you and then it's pointing in the other direction. So this is how we map the magnetic field of the star. We do observe the star when the star is rotating. We take a time series of polarized spectra, and we use a tomographic imaging technique, which is very similar to tomographic imaging used in medicine. And from that, we can reconstruct the magnetic map of the star. So you can know where the magnetic regions are, you can know the field orientation, if it is radial, if it is azimuthal, or what kind of field you have, and you can know the intensity or the strength of the field. And out of these spectra that we collect from a telescope, you could reconstruct the map. And here you have the map in a spherical coordinate system. So you have at the beginning the radial map, then the azimuthal map, and then the meridional map. Throughout this talk, when we have red region, it means that the field is positive, so pointing toward you. And when we have negative, when we have blue region, the field is negative, so it's in the opposite direction. Now, this method, for anyone interested in that, it has its own limitation, we know it. The first limitation, I would say, we would have in this method is that it's really consuming as telescope time. So if you have a star, for example, an F star that is really bright, I will show you one of them now, you would need 3 to 4 observing nights of telescope to be able to reconstruct the map, which is a lot, actually. In addition, there is a little bit more complication, which is it's not you can observe the star for 3 nights and that's it. You have to observe the star when the star is rotating. So if the rotation period of the star is 12 days, you have to observe it almost for 1 month. So you have to split your observations to cover a full month. The other limitation or challenge we have in this method is that this method that is called Zeeman Doppler imaging or ZDI, it recovers only the large scale magnetic field. We cannot recover a small scale magnetic field. Small scale magnetic field, the resolution, we do not have the resolution to cover smaller spots, and sometimes they would cancel out actually in some field geometries. So this is a general introduction for the method. And now I would like to introduce to you how do we actually do it and how do we reconstruct the magnetic map. This is an example for one star, which is HD 189733. It's the one I showed you, the extremely close, the hot Jupiter being extremely close to the star. These observations were obtained in September 2014 using Narval at Telescope Bernard-Milieu in France. So again, the star is orbited by a hot Jupiter. The orbital period is 2.21 days. So imagine you have a planet orbiting every 2 days almost, and the mass of the planet is 1.13 Jupiter mass. You get your polarized spectra, and then you use a technique to get only one profile by extracting the information of every single line approximately you have in your spectra. So these are the polarization profile, the circular polarization profile. In red, you have the observed one, and in black, you have the reconstructed one. So Zeeman Doppler imaging, what it does actually, it reconstructs these profiles, and from the reconstruction, it will give you a map. It will tell you this map will produce those profiles. So as I told you, because we have to observe the star when it is rotating, this star has a rotation period of 12 days. When we have to observe, the star when it is rotating, what the numbers you have here is actually the rotation cycle. So for example, you start with a rotation cycle, let's say of 0.4, and you end up with a rotation cycle of 2.4. So you have to observe the star for 1 or 2 rotation cycles to be able to reconstruct the map. And this is the kind of map we reconstruct. This view might be not very common, but I will explain it to you. So again, we have the radial field of the star, we have the azimuthal field of the star, and the meridional field of the star. But here what we have is a polar view. And I'm sorry, because this is the plot of the paper, so I did not change it to make it more rectangular. But basically what it means, the center of all the circles is the pole, okay? Every circle is separated by the other by a latitude of 30 degrees. So you have 60 degrees, 30 degrees, the thick circle here is the equator, and then you have minus 30 degrees. You cannot see the full star actually because it's inclined, so we don't have all or a lot of information on the side of the star that we do not see indeed. From this kind of mapping, you have all the information you need about the magnetic field. You can know the strength of the magnetic field. In this case, it's about 42 Gauss, which is much stronger than the solar larger scale magnetic field. You can know if the magnetic field is more of a radial field or azimuthal field. In this case, for this particular season, September 2014, we had more energy in the azimuthal component, about 60%. And then you can see if the field is really simple, like a dipolar simple field, or if it is more complicated. And clearly you can see here around the equator many positive and negative regions. So the field in this case was more multipolar field rather than a simple dipolar field. Of course, we have done that for all the stars we had in our sample, but I will not show you all the maps because it can get boring. But the idea is we want to understand if, because of star-planet interactions, if the magnetic field of those stars have particular characteristics, different from other stars that are not orbited by a hot Jupiter. This is the main idea of the project, right? So how do we compare that? Do we take infinite maps and we just look at them? There is another way to do it. And the way to do it is actually, you have to compare, as I told you, you compare them to other stars without hot Jupiters. And I forgot to mention that we got this from the BCool collaboration from Pascal Petier and the collaborators. So this is a collaboration that studies cool stars, full stop. They don't usually have hot Jupiters around because we work in the same consortium. So each one work on his or her let's say. So we will compare the field topology, the strength, if the field is axisymmetric between all of these things, all right? So how do we do that? One of the ways to do it is to try to put all the characteristics we get from the maps in a sort of diagram. And the diagram we have chosen is a diagram that is a mass rotation diagram. So on the y-axis, this is empty for now, but on the y-axis, you have the mass of the star as a function of solar mass. And on the x-axis, you have the rotation period of the star. And what we are going to do now is we are going to fill this diagram with the information we have about stars. What information? We're going to put the intensity of the field, if the field is really intense or not. We're going to describe if the field is radial or poloidal or more toroidal or azimuthal. So the intensity, we're going to introduce it as a size of the element we are using. The fact that it is radial or azimuthal, we are going to use a different color. And then we are going to use different shapes. So if the field is axisymmetric, we will use a round shape. And if the field is non-axisymmetric, we are going to use a star-like shape. So when we put all the stars that we have, including planet hosting stars and stars that are cool stars, not hosting hot Jupiters, this is what we have. So again, this is actually between us collaborators, we call it a confusogram. So I don't want you to get very confused out of it. I just want you to remember a few things. What we care about is how big this symbol is, the color of the symbol, and then the shape of it, if it is more round or more like a star-like. Okay, all the other characteristics are characteristics of the magnetic field, but it's fine. We can remember them later. So if you look at that, you might argue that it's a complete mess and we have everything everywhere. So for example, you would tell me, all right, fair enough. If you take a rotation period of 10 days, you actually see everything happen. Or if you take a mass of one solar mass, you have everything happening. But if we add to this plot one line that will explain the Rossby number, things become a little bit different, I would say. It would stop being a complete mess and start being more clear what's happening at the level of the stars. So what is a Rossby number? Rossby number is simply a description. It's given by the formula that is on the slide. So the rotation period of the star divided by the convection turnover time. Okay, so basically it will describe the rotation of your star and the convection of the star. And this is an important number for people studying magnetic field because it's important for people trying to understand the dynamo actually that are responsible in these cool stars for the generation of the magnetic field. So when you plot a Rossby number here, it's equal to 1. Sorry, I forgot to mention it on the slide. You can see that we do seem to have different magnetic behavior. So stars that are here above this line, they have a Rossby number bigger than 1. They seem to be round, small, and red, whatever that means. And stars that have Rossby numbers smaller than 1, they seem to be bigger, more like a star, and bluer. Okay, so it seems that we have two different characteristics separated by this Rossby number equal to 1. That's fair enough, but then where are our planet hosting stars? I'm presenting them here with their names in green. So you have the stars that we have. We have the sun. I put it as a planet hosting stars actually, not a hot Jupiter, but it's a planet host. And we do see actually that indeed those stars do not seem to have some characteristics that are very far off the characteristics of other stars that do not have a hot Jupiter. So we're not seeing, for example, here Taubu having an extremely big magnetic field with, you know, like a toroidal component, for instance. So we know that star-planet interaction are acting, but they don't seem to affect the characteristics of the larger scale magnetic field of the stars. So this is one conclusion, I would say, of this work. One might ask, fair enough, do we have magnetic cycles? I mean, what you are showing me here is the magnetic field, but do you observe the stars often? Does it change? It's a good question that we need to answer. And this is what we have been doing. We have been following some systems over many, many years. So why would we do that in principle? Because if we look at the sun, we know that the sun has a magnetic cycle. So if we look at the larger scale magnetic field of the sun, which is the polarity, the sun acts as a dipole and it will flip polarity every 11 years. So you would have what I would call like the officially magnetic cycles of 22 years. If you look at the small scale field, so the spots of the star, of the sun, you would see a cycle of 11 years. So for the sun, we know that there is a correlation, let's say, or a relation between those spot cycle, which is 11 years, and the large scale magnetic field cycle, which is a cycle of 22 years. So this is a picture from Sanderson et al. In 2003, where they plot actually the magnetic field of the sun between 2 years, so 97 and 2001. And you can see this is toward the pole. So here it was blue, and then it turned to be red. But in between, actually the magnetic field of the sun becomes a little bit more complicated. So you move from a dipolar field into a more complicated field, and then into a dipolar field, but switched in polarity. So here you can see clearly that it's not a dipole anymore toward the pole. You have like a big many configurations around the equator. So one of the stars we followed up, and I'm going to speak to you about, we did a follow-up for many stars, but this is one of the most interesting, in my opinion. It's called Taubu. It's a planet hosting star. It's an F star, so it has a shallow outer convective envelope. And it has a planet amount that is very massive. The mass of the planet is about 6 Jupiter masses. So it's really very, very massive. The planet is orbiting at around 8.5 stellar radii. So still the planet is very, very close to the star. The very interesting thing about this system that made us really want to study it frequently is that actually the orbit of the planet is 3.31 days. And if you study the rotation period of the star, it is 3.3 days. So it looks like there is a kind of synchronization between the convective layer of the star and the planet. It is possible that it is by pure chance the planet moved here and, you know, we are getting it when it is here. But it might be also that the planet, because it's massive, actually synchronized some part of the star. If you do the calculation for the synchronization of the whole star, it's older than the system, so it's not possible. So the idea was maybe it synchronized the outer convective envelope because of star-planet interactions, which might mean that we have more shearing, friction at the base of the outer convective envelope that we call the tachocline, and maybe it can affect the generation of the magnetic field. We had this idea and we wanted, of course, to explore. So we observed the star frequently. Since 2006, actually, we've been observing it. I am just showing you some of the reconstructed maps, but there are much more. And I don't want really to speak, let's say, about the second and the third. So I just want you to focus on the first row that you have here. So this is per epoch, actually, each one here, each column, let's say, it's per epoch. So this is the reconstruction of the magnetic field in June 2006. This is the reconstruction in June 2007, exactly after 1 year. And this is the reconstruction in July 2008, exactly after 1 year. So you have, again, the radial field in the upper part, then the azimuthal field and the meridional field. I'm just going to focus on the radial field because it applies to the other ones. So if you focus on the radial field, close to the pole, in June 2006, you had a negative field. 1 year later, it switched to be a positive field. And 1 year later, it switched to be a negative field again. So it was the first observation of a magnetic flip of a star other than the sun, with a huge difference that it is happening every year, not every 11 years. So we do have a cycle that is 2 years or shorter. Because of course, when we published this paper back in the time, we only had few observations. So we could not rule out that the magnetic field is shorter. Another thing that is interesting in the star, we observed it actually frequently, and we decided to try to observe between the flips what is happening to the field. So this is here June 2007, July 2008, and in between the star in January 2008. And you could see that while the field was mainly radial, in June and June, the field in January 2008 is mainly azimuthal. Okay, the field that you see here is not a simple dipole, and it's mainly azimuthal. So it seems that when we have the flip, the field is indeed also changing. We don't have a simple flip and that's it. There is something happening in between for the field. So it might be very similar to what we observe on the sun. If we calculate the radial field and the azimuthal field, we do see that they are shifted, the maximum. We do see that they are shifted, and this is what we observe for the sun. We continue to observe the star. I'm not showing all the maps we have, but actually now we know that the magnetic cycle is not of 2 years. The magnetic cycle is shorter. It's a magnetic cycle of 240 days, so 8 months. So this star, every 4 months, it flips polarity. Back in the time when we published this first paper, it was quite a magnetic cycle of 2 years back in the time. We said it's a magnetic cycle of 2 years that could be shorter, of 240 days, and then we found that it is shorter. But it was something because we did not observe such a magnetic, we only knew the sun that takes 22 years. So the other thing was like, okay, does this star show activity variation similar to the sun? So if we study the activity cycles, for stars, we study them, for example, by studying the calcium H and K. Do they show variation? And if they show a kind of cyclic behavior, what is actually the period of the cycle? Before doing this analysis in details that we have done more recently than the first papers, there was, of course, if you want to study the activity, you would go for the archive of Mount Wilson, basically, and you would look for the star in Mount Wilson. Taubo is not a very active star. So for the Mount Wilson, it was not, it was flagged as a not a very active star. So the periodicity was not very clear. However, it was announced that it could be a cycle of 10 years, with a mention of a cycle of 116 days in the papers, but it was not explained because it was like a very weird short cycles that, I mean, they thought actually that it might be something with the analysis more than something happening on the star. So when we analyze data, and the data that we analyzed like span really a long time, and these data, we can use them from the spectropolarimetric data because you have the intensity spectra and you have the polarization spectra. You can also use, of course, archival data. We have found, and this is a work by Matthew Mengel in 2016, we have found actually when you analyze the S index for the star as a function of time, these are the cross, the red cross are actually the observation. And what you have here is the best fit for these observations. And we have found a period of 120 days. Mitag et al. In 2017 analyzed X-ray data for the star, and they had these X-ray data here. They did not fit, but they plotted on top of them a periodicity of 120 days, and they found that it fits well. So it looks that for Taubu, it does actually have a magnetic cycle of 240 days, and it has a cyclic activity cycle of 116 or 120 days, both in the calcium HNK and the X-ray. So it seems that this star has a very similar behavior, magnetic behavior to that of the sun. However, it is 33 times faster than the solar cycle. Why is it faster than the solar cycle? At the beginning, of course, we thought that maybe star-planet interactions, in particular, tidal star-planet interactions might play an important role in that. Now, because we are following other stars, we realize that other F stars do actually, one at least, F star, does actually show a fast cycle, not as fast as Taubu, but still it shows a fast cycle. So this is leading to a kind of better understanding of generation of magnetic field in stars. Is it really tidal, or is it really due to the fact that those F stars have a shallow convective envelope? It's something to be explored by observers, but also by people doing simulations actually of the magnetic field of stars. So I would like to speak also briefly, I would say, about the exoplanet's environment. So we study the magnetic field. Now we know that stars that have that are subject to star-planet interaction, they have general characteristics of the magnetic field that is similar to other stars. Yes, one of them does show a cycle. It might be, or tidal interactions might play a role in that. But what's very interesting when you study the magnetic field of these stars is that the magnetic field is actually, it will affect everything around the star, because it will, cause the magnetic wind. You are going to have all these emissions that will be ejected toward the planets. So anything happening on the orbit of planets, even in our own solar system, it is because, I mean, not anything, but many things happening on the orbit is because of these wind, of this solar wind coming and hitting us. So if we imagine that we have a planet that is only at 8 stellar radii, it is absolutely important to study the environment in which the planet is. So if we take the sun just as an example, of course, this is the sun during the solar minimum and then the solar maximum, and we see the corona of the sun. You do see that you have a different corona. And of course, the different corona is due, actually, a different shape of the corona is due to the fact that you have a different magnetic field. So if you remember when I showed you the magnetic field of the sun, it is more of dipolar here, and it's more of multipolar in the case of the solar maximum. It's important because where the magnetic wind is ejected will depend on this. So for example, when you have those open field lines, you can eject, or the magnetic field will flow along these open field lines, and then it will come to hit Earth or to hit any planet on its way. So different configuration of the magnetic field are very important to understand what is happening, what kind of interactions are happening at the position of the planet. So what do we do if we know the magnetic field of the star? If we know the magnetic field of the star, there are studies about stellar winds that have been going for a long time. But usually people take a simple dipole or a quadrupole and they model the magnetic wind. If you have what we do, if we have the ZDI maps of the star, then actually you can use them as a boundary condition to your model. So regarding when you are modeling the corona, you could use different ways. You could use like stellar wind, or you could use a potential field model. So it's a more simplistic model and computation-wise, it's very fast. But regardless, if you have Zeeman Doppler imaging maps, you can use them as boundary conditions. And this means that you would, in principle, model the corona the best possible way. Rather than saying it's a simple dipole, if you have more of a quadrupole, quadrupole or octupole, then you use these characteristics to model the wind. And we hope it would be actually a more realistic, of course, modeling of the corona. So the way you do it, this is a work by my collaborator, Aline Vidotto in Trinity College. So Aline takes actually the maps, she introduces them in her wind code, because she uses a code to study the wind of stars, and then you can study all the field lines that you have. In addition to that, you can of course study the characteristic of the wind at the position of the planet or anywhere if you wish. So what we are showing you here is actually this dashed line. It is the position of the planet because it's extremely close to the star. And the very interesting thing that we see when we have these octupolar components and that they are not really, the field is not really axisymmetric, you see that the planet at this position that is extremely close to the star, it actually, what you have here is the speed of the wind. It will actually be hit by different, by different speed on its orbit. And it will cross different configuration, different magnetic configuration on its orbit because of its proximity. So we can use these information to try to model what kind of emissions we expect from the planets. This is what we have been doing, in particular in the MOVES program. So I want to talk briefly about it. It's a program that we started some time ago now, where we collected actually spectropolarimetric, UV data, X-ray data, and radio data at the same time for the star. The star is HD 189733. It's a K star, so K2 star. As I told you before, it has a massive planet around it, very close to the star. And the planet is very interesting. It was studied a lot for atmospheric studies, evaporation of the atmosphere. So it is one of the systems that is maybe the most studied in exoplanetary world, let's say. So what we have done for the MOVES program, we observed the stars for different epochs, so 5 epochs, but we had already other observations of the star. So this star, we had observed it for 9 years overall. But here for this particular program, we had 5 epochs of observation. And you can see that you have, like June 2013, August, September, these are 3 months, basically June and July, consecutive months in 1 year. Then you have September 2014 and July 2015. Why do we have these dates? Of course, because we coordinated the spectropolarimetric observations with HST and XMM observations. Interestingly, this star is a K star. It does not show any magnetic field polarity reversal for 9 years, but it does show some changes, in the magnetic field. And what you see here is actually very similar to what I showed you before. So this is the map of the star and then the wind, the field lines that you have. So you have closed field lines in some cases, and then you have the open field lines where the wind actually would be thrown away, let's say, from the star. And the interesting thing about it is that even if you take the star that does not have polarity flip, it is mainly toroidal. The field of the star, usually it's toroidal for most of the epochs, yet only with a difference of 1 month, which is 2 stellar rotation, you do see a completely different configuration of the corona. And you do see it for all the time, for all the epochs actually. So what we have done out of that is that you can actually calculate the magnetic field of the star, let's say, because it will drop, of course, with distance, right? But you can calculate at the distance of the planet, what is the magnetic field of the star. And this is, I think, it's not a complicated, so it's not a complicated plot. You have the longitude of the planet, so the planet on the orbit, and then you have the magnetic field in milligauss here, right? Or in Gauss actually on the picture, in milligauss, sorry. So we have it for many, many epochs because we observed the star, as I told you, for 9 years. But it doesn't matter. If we take only one epoch, we are going to see, as I told you, that actually the planet on the orbit, it will go through different, you know, magnetic, actually the wind, the field of the star will have different strength at the orbit, and it will vary. Not only that, it will vary from one epoch to the other. And here, for example, over all these epochs that we have between 2007 and 2015, we have a mean magnetic field. The minimum of this mean magnetic field on the orbit is 16 and the maximum is 39. What does that mean? It means that actually, if you want to study some emissions of the star, like radio emission, the radio emission of the planet, sorry, if you want to study radio emission, for example, of the planet, it will depend on the magnetic field of the planet and the magnetic field of the star. Now, the magnetic field of the star, we have it because we have ZDI maps. The magnetic field of the planet, we don't have it, so we can suggest it. But once we consider a model for the magnetic field of the planet, we can actually estimate what radio emission we could have, and thus we can plan our observations depending on that. So this is one of the work by Robert Cavana, based on the magnetic, so it's in the MOVES collaboration based on the magnetic map that we have done. What you have up here is actually the radio flux that you would see throughout the orbital phase for different epochs. He only took 3, and we see that the flux, the radio flux that we would have is actually variable on the orbit. It's not, because originally we thought that, okay, if we observe a radio input or a radio, you know, emission from a planet, you would come back, you would see the same one. It's not the case because the flux is variable on the orbit. What you have down is very similar to the previous one, but actually they take the mean value on the orbit. Okay, and we modeled that for different planetary magnetic field of 1 Gauss, 5 Gauss, and 10 Gauss. The very interesting thing here was that all of this is actually within the detection limit of LOFAR. So with LOFAR, there is no detection yet officially announced, but we are still hoping to detect radio emission from exoplanet. The other interesting thing to know is that if you detect a radio emission from the exoplanet, then if we go back to this one here, if you detect a radio emission, B of the planet is unknown, but you can use the formulas that I don't show here. I don't like to show a lot of formulas. But if you have the radio emission and you have B of the star, you can deduce the magnetic field of the planet. And this would be the first probably detection, that like kind of direct detection of the magnetic field of a planet. Because for now, we can estimate, we can try to think what kind of magnetic field the planet would have, but we do not have direct observations of that.
We have about 2 minutes left.
Sure. So I just briefly, I thought I would actually finish in 25 minutes, I told you, but it doesn't seem I did. So briefly about habitability, this is something also for the future. So many missions now, they are looking for habitable planets around very cool stars. Why is that? Because the habitable planets, we imagine that they should have liquid water on top on their surface. So if the star is cool, like an M dwarf, the habitable zone would be really close to the star. So you can observe your planet because it will have a fast orbit. You can observe it many times and you can actually confirm it. The problem with M dwarf is that they have a very strong magnetic field, and this is really for the future. I'm not going to talk a lot about it, but it's something that we have to consider. If you have a very strong magnetic field and wind, how does it actually affect your habitable zone? And do you actually have a planet? What kind of shield does the planet have in order to stay habitable? And that's it. I will leave you here with the conclusion and maybe with this NASA simulation of the wind, of our wind, actually of the solar wind hitting Earth and getting deflected by the magnetic field of Earth. And that's it. Thank you so much.
All right, thanks a lot. On behalf of the audience, I am clapping. Thanks for the great talk. I think Srini had a question, he typed it. So
yeah, thank you. Thank you so much for the great talk, but I wrote down the question in the chat.
Sure, so I have to check. Maybe I can stop sharing to get to the chat.
Yeah.
All right, here we go. So.
I could ask you.
Sure.
You mentioned the magnetic interactions for the tackle line for Taubu. Now,
Yes.
are there similar magnetic interactions possible for the sun, let's say from Jupiter? I know some work has been done, but I don't know what the prevailing wisdom is.
So the thing is that the difference between Jupiter and Taubu is that Jupiter has one Jupiter mass and it is at 5 astronomical
units. I totally understand that, yeah.
You know, so I am not sure actually. I do remember that there are some effects, but I'm not sure that they would be really affecting much. I have to double check that.
Most
because you know, if we think, yeah, sorry, I'm interrupting, but if we think about tidal interactions being at role, no, it's less massive and further away. So I'm not sure that it would really, I mean, Jupiter to the sun as Taubu B to Taubu. The other thing is that actually, because Taubu is an F star, the convective outer layer is quite thin. So if you compare the mass of the planet to the mass of the outer convective layer, it would be important. Yes. And so this is one of the reasons we thought it might actually be playing a role. But again, the other thing is that maybe it's playing a role, but I'm not sure it's the only reason, because now with other F stars that at least one or two, one's F star and one K star, actually, they do not have a hot Jupiter amount. And we started seeing, because we are monitoring since some time, you know, we started seeing flips. So
the calculations that I know people make assume a certain average strength of the magnetic field. But in general, magnetic fields are very intermittent and there are very intense activities in localized regions. And I don't know whether such calculations have been made. I should ask somebody who does these things directly.
So you mean for the interactions with the...
Yeah, exactly.
Yeah.
Anyway, thank you so much for this very nice talk.
Thank you. Thank you.
Yeah, we have next question from Axel. I have unmuted you. Please go ahead.
Yes. Thanks very much, Rim, for a very interesting talk. I would like to ask whether you begin to have butterfly diagrams for some of the stellar magnetic fields, either in time latitude as for the sun, or in time longitude, which would be appropriate for non-axis symmetric stars, which we expect to occur for these rapidly rotating ones.
Okay, sure. So the thing is that for now with Zeeman Doppler imaging, you know, we can only have the largest scale magnetic field. So if you want to check the butterfly diagram, I would say you would need probably very like fast rotating stars. And I don't think that we have anything, you know, like I'm not aware that we do have similar things for the moment. I think we probably do that maybe for planet hosting stars, especially because, you know, like to detect the planets, now there is a lot of modeling about where the spots are. I have to look into that, but for the stars that we are working on, I'm not aware that we do have that, no.
I mean, measuring the large scale field is fine. That's exactly what one needs, but one needs a sufficiently long record, and one actually also ideally would like to average so that you really only take the largest possible scales, that you really see something systematics. Otherwise, you don't see the systematics. You just see a lot of little pictures here and there, and you don't see really what's the systematics behind it.
So let me please ask you to make sure I understand. So the idea is that rather than taking the largest scale field, you would really squash, let's say, right, the star.
We would in that. So if you have a solar butterfly diagram, we would average over longitude. So that means we would lose all the information in longitude, but we will gain that we learned for the first time in that case that there is a magnetic field which propagates to the equator. That you can only see if you really average sufficiently.
Sure. I'm not aware that actually,
back then.
Yeah, I'm not aware actually that this has been done. But again, I think that it wasn't done because, you know, it's the largest scale magnetic field, so we wouldn't really be seeing that. But yeah, it's something that we can actually explore.
Okay.
Some work that there are some work linking what we know from the activity papers, you know, and the activity studies actually with the largest scale magnetic field. So are they on the active branch or inactive branch? What kind of magnetic field you would have? We have seen, this is a work done by Victor C. And we have seen that, for example, stars that show a magnetic cycle, they will be in the inactive branch rather than the stars showing that don't show a magnetic cycle. They are more toroidal, they are on the active branch. But I'm not aware of you know, like a butterfly-like diagram.
Okay, thanks.
Yeah.
Sorry, yeah, we have another question from Mohammed Abbas. I'm unmuting you, so go ahead and ask your question.
Yes, hi. Thank you, Reem, for the interesting talk. And I was just saying it's interesting how you can find information about possible or about exoplanets in general just by studying the magnetic fields of stars. But when it comes to the plot you showed for the rotation versus the mass, where does this Rossby number come from? And also, so I guess if you know the rotation period of a star and the mass, you can predict whether that star would have a planet, a Jupiter-like planet, without having to get any information other than the rotation and the mass, rotation period and the mass?
Yeah, so actually when we plot this, it's only purely magnetic characteristics, regardless if it has a planet or not.
Yeah.
The Rossby number itself, it really explains, and I think people in the audience maybe can even explain it better. It really explains actually the rotation of the star, and those stars are cool stars. The outer layer it's convective. So basically, you see the rotation, the effect on the rotation and the convection. And we know that, in these stars, the magnetic field is produced by dynamo effects. Originally, we thought it's at the base, but there are some studies that say it's in the whole convective region. So when we do this kind of study, we somehow don't care if the planet is there or not.
Okay.
Now, okay, so the Rossby number will explain this effect of rotation. There have been studies, for example, that showed, one of them was Pascal Petit, that showed if the star rotates more rapidly.
Did we lose?
A toroidal field. Okay, some people, as I told you, like they can take the rotation, actually, you consider less than 12 days or more than 12 days, and you see things happening. All right. Now, if you have a hot Jupiter around, clearly the general characteristic is not varied. So it's similar to other stars that don't have hot Jupiters. So I don't think you can really study, like, you can take the characteristics of the magnetic field to say if you have a hot Jupiter or not. The other thing, hot Jupiter are quite easy to discover because they are big and close. So they would have an effect that is really clear in the radial velocity. If you are discovering your stars via radial velocity or transit, you would see a clear signature for them. So I don't think hot Jupiters, we should really worry about, discovering them through such an indirect way, I would say.
Yeah,
but in all cases,
right,
sorry.
yeah, but there are like 4,000 or less confirmed exoplanets.
But not all of them are hot Jupiter.
Sure, yes, of course.
Yeah, so now, for example, now the big thing in exoplanet studies is actually to find smaller planets around cool stars that could have life, okay, so the habitable planets. And these ones are very small planets. So to the opposite of hot Jupiters that are big, you would want for these planets, you would want to understand the effect of the magnetic field, because magnetic spots would mimic a planet around the star. So you would want to understand the effect of the magnetic field to get rid of it in order to discover the planets. But for hot Jupiter, this isn't really a big problem, I would say.
Okay. Thank you.
You're welcome.
All right. Thanks a lot, Reem.
Thank you so much for having me.
See you all next week.
Thanks a lot. Okay. Bye.
Right.
See you. Bye.
Yeah.